Alright, so let's talk about the Nernst equation lab. Basically the lab where you're looking to find the reference potential and the number of electrons transferred between the reaction of copper and zinc. Now the reaction you're studying here is actually, just make sure I'm saying it right, the oxidation of zinc using a copper plus 2 cation. Now, we have to write this reaction reversibly, even though it is effectively an irreversible reaction because of the energy difference between the reactants and the products. But what we're looking at here is a cell created by two solutions. So we've got one solution of copper plus 2 ions with copper, and one solution of zinc plus 2 ions with zinc. We've got our zinc electrode, copper electrode, and we're going to connect the two, and between the two, we've got our voltmeter, which can measure the voltage, and also between the two, we've got our salt bridge here. And our salt bridge is we allow the ions to flow from one to the other to make sure that we preserve charge potential. Because keep in mind, we have electrons moving from zinc to copper. And those electrons are going to build up a negative charge in the copper cells, so we actually need the anions, the chloride ions, to actually move from the chlorine side to the zinc side to make sure we don't kind of get this charge buildup. Now, to do this lab, you're going to use the Nernst equation. What the Nernst equation tells us is that the voltage or the electrochemical potential of a cell, so an oxidation reaction paired with a reduction reaction, is equal to the reference potential, E naught cell, minus RT over NF ln of Q. And for this reaction, your Q here is the concentration, Zn plus 2, over the concentration of the Cu plus 2 and their respective cells. So, what you're going to measure in this lab is the actual voltage, and you're going to control the concentration of zinc and copper. And this will give us a linear plot. Our voltage is the Y, our X is our ln of the concentration of zinc over copper, and this means that our slope here is equal to minus RT over NF, and our y-intercept is equal to the reference potential. So how do we do this in practice? Well, what you're going to do is you're going to measure the cell potential, you're going to measure the voltage between the two half cells that you're creating, the zinc and the copper cells, and you're going to calculate Q for each one, and you're going to generate this plot. So X is your ln of Q, Y is your measured voltage, and you're going to do a linear regression. And we're going to do this by keeping one of the concentrations constant. So for one set, you're going to keep zinc concentration constant. For the other set, you're going to keep the copper concentration constant. And you're going to get two plots. The slope, the y-intercept of both here is going to be, when you do it, is going to give you your cell potential. And the other thing to keep in mind is that because we have zinc and copper on numerators and denominators, they're also going to have opposite slopes, meaning that the voltage will go up, becomes a more favorable reaction. If we are increasing the copper concentration, the reaction is going to become less favorable as we decrease the zinc concentration. So this is kind of the gist of the lab. Measure the voltage at given concentrations, plot ln of Q versus the measured voltage, and use the slope and the y-intercept to figure out the reference potential as well as the number of electrons transferred.